Right now, somewhere inside the churning golden clouds of Saturn, drifting as scattered atoms mixed permanently into a hydrogen and helium atmosphere, is a machine that used to be a spacecraft. It has no shape anymore. No solar panels, no antenna, no cameras. It vaporized in less than a minute, 91 seconds to be exact, traveling at roughly 70,000 miles an hour, tearing itself apart in the upper atmosphere of a planet it had spent 13 years quietly falling in love with. And in those last 91 seconds, as its small thrusters fired themselves into oblivion just to keep an antenna pointed at a planet nearly a billion miles away, that dying machine sent back more real scientific data per second than almost any other moment in the history of planetary exploration. Not a warning, not a distress signal. Actual measurements, actual atmosphere samples, actual physics, transmitted in real time by a spacecraft that knew, in whatever sense a machine can know anything, that it was never coming back. This is the story of Cassini's final seconds at Saturn. And here is the part almost nobody talks about. What that spacecraft found in its last moments and in the years of data it sent home before that plunge did not close the book on Saturn. It cracked it open in ways scientists are still, right now in 2026, struggling to explain. Stay with me, because by the end of this, you're going to understand why a machine that died 9 years ago is still generating brand new scientific papers today, and why some of what it found breaks rules of physics that were considered settled a century ago. If you want more stories like this one, the kind grounded in real, published research instead of exaggerated headlines, go ahead and hit subscribe now, because we are only getting started. Let's go back to where this actually begins. October 15th, 1997. A Titan IV rocket lifts off from Cape Canaveral, Florida, carrying the heaviest interplanetary spacecraft ever built at that point, a machine roughly the size of a school bus, weighing more than 6 tons fully fueled, named Cassini after the Italian astronomer who first spotted the gap in Saturn's rings 3 centuries earlier. Bolted to its side is a smaller probe called Huygens, built by the European Space Agency, designed to do something no human object had ever done, land on the surface of a moon in the outer solar system. The plan sounds almost absurd when you say it out loud. Fly for nearly 7 years, using the gravity of Venus twice, then Earth, then Jupiter, just to build up enough speed to reach Saturn at all. No spacecraft before or since has needed that many gravitational slingshots just to arrive somewhere. And when it finally did arrive, breaking into orbit around Saturn on June 30th, 2004, it became only the 4th spacecraft in history to visit the ringed planet and the very first to actually stay. What followed was 13 years that fundamentally rewrote what humanity understood about Saturn and its family of moons. In January of 2005, the Huygens probe separated from Cassini and descended through the thick orange haze of Titan, Saturn's largest moon, sending back the first and still only images ever taken from the surface of a world in the outer solar system. What it found was a landscape that looked almost unsettlingly like Earth. River channels, drainage networks, rounded pebbles shaped by flowing liquid, except every drop of that liquid was not water, but methane and ethane, hydrocarbons that behave as liquids only because Titan's surface sits at nearly minus 180 degrees Celsius. Cassini itself, orbiting overhead for over a decade, would go on to map that moon's hydrocarbon lakes and seas in detail, some of them larger than the Great Lakes of North America, confirming Titan as the only other place in the solar system known to have stable liquid on its surface. Then, in 2005, Cassini turned its instruments toward a tiny, unassuming moon that nobody had expected much from at all, a bright, icy world called Enceladus, barely 300 miles across. And what it found there rewrote the entire conversation around life in our solar system. Plumes of water vapor and ice erupting from cracks near the moon's south pole, geysers blasting material hundreds of miles into space, coming from what turned out to be a vast liquid ocean hidden beneath miles of ice. Now, before we go further into what happened at the very end of this mission, here's something worth pausing on, because it changes how you should think about everything that follows. Cassini was never supposed to last this long. Its prime mission was budgeted for 4 years. NASA extended it once, then extended it again, ultimately stretching a 4-year mission into a 13-year marathon that returned more than 500,000 images and generated thousands of scientific papers, a number that, as you'll see later in this video, is still climbing in 2026, 9 years after the spacecraft itself ceased to exist. But by 2017, Cassini was running out of the one thing no amount of extension could replace: fuel. And this is where the story most people think they know actually gets far stranger than the version usually told. Here's the problem NASA's mission planners faced. Cassini had almost no propellant left to maneuver. Left uncontrolled, its orbit would eventually become unpredictable, and there was a real non-zero chance that an unpiloted dead Cassini could eventually drift into and collide with either Enceladus or Titan, The 2 moons the mission itself had just proven were genuinely capable of hosting the ingredients for life. Enceladus, with its buried ocean and hints of hydrothermal activity on its seafloor. Titan, with its thick atmosphere and decades of complex organic chemistry, constantly raining down onto its surface. A spacecraft built on Earth, covered in whatever microorganisms might have survived nearly 2 decades of space travel, crashing uncontrolled into one of those worlds, was considered an unacceptable risk to the integrity of future life detection missions. So mission planners made a decision that sounds almost poetic once you understand the reasoning behind it. Rather than let Cassini die quietly and unpredictably, they decided to kill it deliberately, on their own terms, in the one place in the Saturn system where it could never contaminate anything that mattered: Saturn itself. That decision produced what NASA named the grand finale, and it remains one of the boldest things any spacecraft has ever been commanded to do. Beginning on April 26, 2017, engineers directed Cassini into a series of 22 orbits that threaded it through a gap roughly 1,200 miles wide, the narrow space between the top of Saturn's atmosphere and the inner edge of its rings. No spacecraft had ever flown there before. Nobody actually knew for certain what was in that gap. Models suggested it should be relatively empty, but there was a real chance it was filled with ring particles large enough to seriously damage or even destroy the spacecraft on contact at orbital velocity. For the first several of those dives, Cassini flew with its large dish antenna angled forward like a shield, blind, unable to communicate with Earth, simply trusting the models that said the gap was survivable. It survived, and then it kept surviving, week after week, for 5 months. And what it found during that final stretch is where the actual science of this story gets extraordinary, because it is not, contrary to what the more sensational corners of the internet like to suggest, a story about a single hidden secret. It is a story about at least 4 separate, genuinely unresolved mysteries about Saturn that Cassini's last months of life either created or deepened, mysteries that working scientists are still actively arguing about right now in papers published in 2025 and 2026, years after the spacecraft that started the argument no longer exists in any recognizable form. The first of those mysteries sounds almost embarrassingly basic once you hear it, and that is exactly why it matters so much. We do not actually know, with confidence, how long a day is on Saturn. That might sound impossible. We have sent multiple spacecraft to this planet since the 1980s, but Saturn has no solid surface to track, no fixed landmark you can time a rotation against the way you can with Earth or Mars. For decades, scientists relied on radio emissions coming from Saturn's magnetic field, a signal called Saturn kilometric radiation, using its periodic pulsing as a proxy for the planet's rotation. Voyager 2 measured that period back in the early 1980s and got 10 hours, 39 minutes, and 22 seconds. Then Cassini arrived decades later, measured the exact same kind of signal using the exact same method, and got 10 hours, 47 minutes, 6 seconds, nearly 8 minutes longer. That is not supposed to happen. A planet's deep rotation rate should not measurably drift within a few decades. What scientists eventually realized is that the radio signal was never actually timing the planet's rotation at all. It was timing something happening in the plasma of Saturn's magnetosphere that merely drifts in sync with rotation, loosely, and that drift itself changes over time for reasons still not fully understood. So researchers turned to something almost nobody would have guessed could work: the rings themselves. Saturn is constantly vibrating, extremely subtly, oscillating internally the way a bell rings after being struck. Except these vibrations move the planet's surface by roughly a meter every 1 to 2 hours, far too small to see directly. But those internal oscillations tug gravitationally on the icy particles in Saturn's rings, and that tug creates faint spiral density waves rippling outward through the rings, waves that Cassini's instruments spent 13 years quietly documenting in extraordinary detail as it watched stars flicker behind the rings during hundreds of stellar occultations. In 2019, a researcher named Christopher Mankiewicz, then at the California Institute of Technology, used those ring waves essentially as a seismograph, turning Saturn's own rings into an instrument for listening to the planet's interior the same way seismologists use earthquakes to map the inside of the Earth. What that analysis produced was a new estimate for Saturn's rotation: 10 hours, 33 minutes, and 38 seconds, several minutes faster than either of the previous radio-based estimates, and more importantly, derived from a completely different physical principle. As of the most recent published analyses, stretching into 2026, that seismological figure remains the most physically grounded estimate scientists have, yet it still carries real uncertainty. And the older radio-based numbers are still cited in textbooks and mission planning documents because no single measurement has been declared definitively correct. In other words, more than 4 decades and multiple spacecraft into visiting this planet, we still cannot tell you with total confidence exactly how long a single day lasts on Saturn. And that single unresolved number cascades into nearly everything else we try to calculate about its interior. The second mystery goes even deeper, literally, into the question of what Saturn is actually made of at its core. For most of the 20th century, the standard model of how a gas giant forms involved a compact rocky core forming first, then attracting a massive envelope of hydrogen and helium gas around it, like a snowball that first needed a hard center before it could grow. That same ring seismology data Mankiewicz used to measure Saturn's rotation also let him, working alongside Caltech astrophysicist Jim Fuller, probe the deep interior in far more detail than gravity measurements alone ever could. What they published in 2021 in the journal Nature Astronomy did not describe a compact solid core at all. It described something researchers now openly call a fuzzy core, a diffuse, slushy mixture of ice, rock, hydrogen, and helium with no sharp boundary anywhere inside it, gradually thickening in density as you move toward the planet's center, extending outward across roughly 60% of Saturn's entire radius, nearly 35,000 kilometers, more than 5 times wider than the whole planet Earth. Within that fuzzy region sits somewhere around 17 Earth masses worth of rock and ice, dissolved and mixed into the surrounding gas, rather than sitting as a distinct object, bringing the total mass of that diffuse central region to roughly 55 Earth masses, more than half of Saturn's entire mass. Mankiewicz described it plainly at the time, saying the hydrogen and helium gas in the planet gradually mixes with more and more ice and rock as you move toward the center, comparing it to parts of Earth's oceans where salinity increases the deeper you go. That single discovery quietly overturned decades of assumptions about how giant planets form, not just Saturn, but potentially Jupiter too, and by extension, the thousands of gas giant exoplanets astronomers are now cataloging around other stars, planets we can never send a spacecraft to, but whose interiors we now suspect may follow the same fuzzy, gradual pattern, rather than the clean layered model textbooks taught for generations. The third mystery is arguably the strangest of the four, because it involves a rule of physics that was considered essentially settled science since 1933. That year, a physicist named Thomas Cowling proved something called Cowling's theorem, which states, in essence, that a magnetic field generated by a rotating fluid dynamo, the process believed to generate the magnetic fields of every planet with one, cannot remain perfectly symmetric around the planet's spin axis. There always has to be some tilt, some wobble, some asymmetry, or the dynamo mechanism generating the field should not be able to sustain itself at all. Earth's magnetic field, for reference, tilts about 10 degrees from its rotation axis. Jupiter's tilts a similar amount. Uranus and Neptune are wildly tilted, nearly 50 degrees in some cases, with messy, complicated field structures. When Cassini's magnetometer took its closest ever measurements of Saturn's magnetic field during those final grand finale orbits, threading directly through the region between the planet and its rings, it measured a dipole tilt of less than 0.007 degrees, functionally zero. The most axisymmetric planetary magnetic field ever measured anywhere in the solar system, arguably in violation of a rule of physics that had gone essentially unchallenged for close to 90 years. Researchers have proposed an explanation that a thick, stably stratified layer of electrically conducting gas sitting above the actual dynamo region, more than 2,500 kilometers thick, according to some models, could be smoothing out and shearing off any tilt before it becomes visible from the outside, effectively hiding the asymmetry that Cowling's theorem demands must exist somewhere. But that explanation remains a hypothesis, not a confirmed mechanism, and as recently as papers published in 2022, scientists were still building entirely new dynamo simulations, specifically trying to reproduce Saturn's bizarre near-perfect symmetry from first principles, without fully succeeding in explaining why the effect is quite this extreme. Saturn's magnetic field, in other words, looks almost too clean to be real, and nearly a decade after the spacecraft that measured it burned up in the planet's clouds. Nobody has fully explained why. Now, here's a question worth sitting with for a second before we move to the fourth mystery, and I genuinely like to know what you think. Of everything we've covered so far, the missing hours in a Saturnian day, the fuzzy core dissolving the line between rock and gas, or a magnetic field that seems to defy a physics rule nearly a century old, which one surprises you the most? Drop a comment and let me know, because it genuinely shapes which of these threads deserves a deeper follow-up video down the line. The fourth mystery is the one that has generated the most public attention, and it concerns the rings themselves, the single most recognizable feature in the entire solar system. During those final 22 dives, Cassini passed directly between Saturn and its rings repeatedly, allowing radio signals sent to and from the spacecraft to be subtly tugged by the combined gravity of the planet and the rings together. By measuring those tiny accelerations, changes in Cassini's velocity of a fraction of a millimeter per second, detected across a distance of hundreds of millions of miles, scientists were able to directly weigh Saturn's rings for the first time in history. The answer, published in Science in January 2019 by a team led by Luciano Ies of Sapienza, University of Rome, came out to roughly 15.4 million billion metric tons, only about 40% the mass of Saturn's small moon Mimas. That number mattered enormously because ring particles are made almost entirely of bright, reflective water ice, and interplanetary dust is constantly raining down onto them, gradually darkening them over time. A ring system as old as Saturn itself, some 4.5 billion years, should statistically have accumulated enough dark contamination by now to look considerably dingier than what Cassini's cameras actually photographed. Combined with that newly measured low mass, the numbers pointed toward rings that are astonishingly young, forming somewhere between 10 and 100 million years ago, meaning Saturn spent most of its 4.5 billion year existence with no rings at all, and that the rings we see today may have formed sometime during the age of the dinosaurs here on Earth. That finding alone would have been remarkable enough to close the story, except it didn't close anything. Researchers studying that same grand finale data soon discovered something called ring rain, material, mostly water ice, mixed with more complex organic compounds, constantly leaking out of the rings and spiraling down into Saturn's upper atmosphere along magnetic field lines, falling at a rate some early estimates placed as high as 10 tons of material every single second. That discovery immediately complicated the age question, because if the rings are actively losing that much mass continuously, then whatever we measure today has to be smaller than what existed originally, which either means the rings are even younger than the 10 to 100 million year estimate to account for how much material has already rained away, or more unsettlingly, that they could actually be far older than that estimate and simply appear artificially young because so much of the original contaminated material has already drained out of them and burned up in Saturn's clouds. As recently as 2025 and 2026, planetary scientists, including researchers publishing new dynamical models of the broader Saturn system, have continued actively debating this exact question, with some papers supporting a genuinely young ring system formed from a shattered comet or destroyed icy moon, and others arguing the true picture is still muddier than the clean, headline-friendly answer everyone wanted. As one planetary scientist memorably put it when discussing this exact controversy, if you search online for how old Saturn's rings are, you'll get a suspiciously confident-sounding answer, when the honest answer, even today, is that nobody fully agrees. That ring rain discovery led to something else nobody fully expected either, a direct chemical sampling of what is actually falling out of the rings and into Saturn's clouds. Cassini's ion and neutral mass spectrometer, sniffing the atmosphere directly during those final close passes, expected mostly water and simple silicate dust. What it found instead was a genuinely surprising cocktail, complex organic compounds embedded inside tiny grains of water ice, alongside methane, ammonia, carbon monoxide, molecular nitrogen, and carbon dioxide, all raining down together from the rings into the planet below. What made this particularly strange is that the composition of those falling organics turned out to be measurably different from the organic chemistry Cassini had already documented separately at Enceladus and separately again at Titan, suggesting Saturn's system contains at least 3 distinct, chemically separate reservoirs of organic material, one in the rings, one on Enceladus, one on Titan, each apparently evolving its own chemistry largely independent of the others despite existing within the same relatively small neighborhood of space. Nobody built that into their models beforehand. Nobody expected Saturn's rings to be actively contributing their own unique flavor of prebiotic chemistry directly into the planet's atmosphere in real time for as long as the rings continue to exist. If you're finding all of this as strange as I did putting this together, this is a good moment to hit that like button, because it genuinely helps stories built on real published research, rather than exaggerated clickbait, reach more people who'd actually appreciate hearing it explained properly. Now, let's actually go back to September 15th, 2017, and walk through what the final hours of this mission genuinely looked like, because the real sequence of events is more gripping than most fictional versions of a spacecraft's death you'll ever read. In the days leading up to the plunge, mission controllers commanded Cassini to capture what they internally called the last picture show, a final set of images of Saturn, its rings and the moons, Titan and Enceladus, deliberately captured and transmitted home before the spacecraft reconfigured its systems for a different kind of transmission entirely, one designed for real-time science data rather than stored images, because there would be no time left afterward to send anything back later. On its very last orbit, high above the planet, Cassini crossed the orbital path of the F ring, the outermost of Saturn's main rings, for the final time at 3:22 in the morning Eastern Time. From that point forward, there was no possibility of turning back. At 6:31 that morning, Saturn spacecraft time, Cassini began entering the uppermost, thinnest wisps of Saturn's atmosphere, roughly 1,190 miles above the visible cloud tops, an altitude where the atmospheric pressure was still comparable to sea level pressure back on Earth, deceptively gentle sounding for what was about to happen. Small attitude control thrusters, the same kind used for years to make tiny course corrections, began automatically firing to keep Cassini's large dish antenna locked onto Earth as atmospheric drag started very slightly tugging the spacecraft off course. At first, those thrusters worked easily, firing at around 10% of their total capacity. But atmospheric density increases exponentially, not gradually, and within about a minute, the drag had increased so much that the thrusters were forced to ramp all the way up to 100% capacity, just to hold the antenna steady. Even firing at full strength, they could only compensate for so much. Engineers had calculated in advance, based on how the thrusters performed and how quickly the atmosphere was expected to thicken, that Cassini would likely survive somewhere between 30 and 90 seconds inside the atmosphere before finally losing the fight and tumbling out of alignment with Earth. In the actual event, it beat even the optimistic end of that prediction, holding its orientation and continuing to transmit clean, readable data for a full 91 seconds, 30 seconds longer than mission planners had dared hope for beforehand. During those 91 seconds, 8 of Cassini's scientific instruments remained fully active, sampling the composition of Saturn's atmosphere directly for the first time in human history, at depths no spacecraft, Voyager included, had ever reached before or has reached since. This was, deliberately, the highest priority science of the entire grand finale, sampling gases, plasma, and particles at exactly the altitude scientists needed to understand how Saturn's deep atmosphere behaves and what it's actually composed of. In the final 20 seconds or so before contact was ultimately lost, with the thrusters already maxed out and unable to compensate any further, Cassini began to lose the battle. Telemetry data started to noticeably degrade first, as the antenna's precise pointing accuracy began slipping. Then, in the final 8 seconds, the spacecraft began tipping backward, its radio beam physically sweeping away from Earth's direction entirely. The structured data stream vanished first. A bare, unstructured carrier signal, essentially just a raw tone with no information encoded on it anymore, lingered for a moment longer. And then that too disappeared completely. Because Saturn sits nearly 1 billion miles from Earth, the actual moment of loss of signal at the planet itself, roughly 6:32 in the morning, spacecraft time, did not reach human ears until 83 minutes later, at 7:55 and 16 seconds Eastern Time, when the last trace of Cassini's carrier signal finally arrived at the Deep Space Network's giant dish complex near Canberra, Australia, and was confirmed lost. In a very real sense, by the time anyone on Earth actually knew the mission had ended, Cassini had already been part of Saturn's atmosphere for well over an hour. Julie Webster, the mission's spacecraft operations chief, who had worked on Cassini for decades, summed up what nearly everyone on the team felt in that control room with a simple, repeated sentence that has since been quoted in nearly every retrospective written about the mission. "It was a perfect spacecraft," she said. "Right to the end, it did everything we asked it to. It's perfect. It's perfect. What's worth understanding is that Cassini's destruction was never simply about generating one final burst of dramatic data, even though it did exactly that. It was fundamentally an act of planetary protection, a deliberate decision to sacrifice a spacecraft that had already exceeded every original expectation placed on it, specifically to guarantee that Enceladus and Titan, the two worlds Cassini itself had proven were genuinely capable of hosting the chemistry and possibly the conditions for life, would remain uncontaminated for whatever future mission eventually goes looking more directly. If a future spacecraft ever does drill into Enceladus's ice, or sample its ocean directly and finds something that looks biological, that result needs to be trusted as something that actually originated on Enceladus, not something accidentally carried there decades earlier from Earth. Cassini's fiery ending, in that sense, wasn't really an ending for the search for life around Saturn at all. It was mission planners deliberately clearing the path so that search could still be taken seriously by whoever attempts it next. And that search for what happens next is very much still unfolding right now in ways that connect directly back to the mysteries Cassini left behind. In 2026 alone, new peer-reviewed papers have continued extracting fresh insight out of a data archive from a spacecraft that no longer physically exists. Researchers have published new work modeling Enceladus's interior structure, using electromagnetic induction techniques applied to Cassini's old magnetometer readings, refining exactly how deep and how salty that moon's hidden ocean really is. Other teams have published new comparisons of Jupiter's and Saturn's satellite systems, using Cassini data alongside newer observations to explain why the two largest planets in our solar system ended up with such different families of moons. Still more recent papers have gone back through Cassini's multi-instrument observations, specifically looking for evidence of an extended interaction between Saturn's magnetic field and Enceladus, refining our understanding of exactly how that little ocean moon punches so far above its weight inside Saturn's vast magnetosphere. None of these researchers had access to a working spacecraft. Every single one of them is working entirely from data that a machine, already torn apart and mixed into Saturn's clouds 9 years ago, managed to send home before it disappeared.